Lesson 4.3, Graphing Linear Non-Proportional Relationships Using Slope and Y-Intercept. Lesson 4.3, Graphing Linear Non-Proportional Relationships Using Slope and Y-Intercept. Using slope-intercept form to graph a line. Recall that y equals mx plus b is the slope-intercept form of the equation of a line. In this form, it is easy to see the slope m and the y-intercept b. So you can use this form to quickly graph a line by plotting the point 0b, that's a fancy way of saying plotting the y-intercept, and then using the slope to find a second point. All right, let's take a look at the video for example 1.
Hey, I love going to arcades. In fact, it's sort of great, the noise and stuff. Look how exciting it is back there. In fact, I want to go there and play. In fact, let's forget this lecture and well, no, I'll come back and show you this, but it's sort of fun back there too. I'm going to do that later. All right, so here's a fun fact about a particular arcade that I'm thinking about. So an arcade deducts 3.5 points from your 50-point game card for each skittleball game you play. Okay, the linear equation y equals negative 3.5x plus 50 represents the number of points y on your game card after you've played x number of games. So the issue for us to think about is, how can we graph the equation using the slope and y-intercept? Okay, so let's check it out. So here is the function y equals negative 3.5x plus 50. Now, what I know here is, remembering the slope-intercept form, that the slope is equal to negative 3.5, and the y-intercept is equal to 50. So immediately I see the y-intercept is 50, so on the y-axis, I know we're going to cross it at 50. I also know that the slope is going to be negative 3.5. So what does that mean? Well, that's the slope, which means it's the rise over run. The rise over run. So how could I write this? Well, I could actually write that as a fraction. So as an equivalent fraction, this would be negative 35 over 10. And now the rise over run is a lot more clear. What does the rise mean? That means what we do in the y direction, that's sort of the rise, and the run means this way back and forth. Now notice that the numerator is negative 35. That means that actually, even though we're calling it rise, it's not going to be an increase. But since it's negative, we're going to drop. We're going to drop 35, and then this positive 10 in the denominator means we're going to go in a positive direction 10 units that way. So what we're really doing here is we're saying, okay, if we know a point on that line, which we do, then from that point, if I drop 35 units in the y direction, 10, 20, 30, 5, and move over 10 units in the x direction, so that's 10, then that is a point on the line. So that point must be on the line. Let me say that again. I start from my known point, which in this case is my y-intercept, and this tells me rise over run. The negative means I go down 35, 10, 20, 30, 5, and then I go over 10 units in the x direction, 10, and that point's on the line. That's what slope means. And now, if I have 2 points, of course, I know the line. 2 points determine a line, and I can graph the line perfectly. There it is. And so there is the line. They asked us to graph the equation using the slope and the y-intercept, and we just did that. So it's really cool. So even though the sounds and the bells and the whistles of the arcade are going back there, the point is all the excitement's right here because we're using slope-intercept form. Fun stuff.
All right, now for those of us who are a tad bit confused, we're going to break it down a little bit more for you. All right, now don't forget, we're following our equation, which is y equals mx plus b. So m is our slope, negative 3.5, and b is our y-intercept. Okay? Now the easiest thing to look at first is going to be the y-intercept. See that 50? That means that the point is going to cross, the line is going to cross the axis, the y-axis at 50. So we can just plot that point. Now notice this occurs when x is 0. Right, this occurs when x is 0. So if we plot 50 right here, notice the x value is 0. All right, next let's look at the slope. We said the slope was a negative 3.5, so m is equal to a negative 3.5. Now don't forget, slope is what? Rise over the run. So 3.5 is our rise, negative 3.5 is our rise, and there's no number that we see on the bottom, so we know that's going to be the run, and it's going to be 1. So m is equal to a negative 3.5, which is equal to a negative 3.5 over 1. A negative 3.5 over 1. Now I want to graph this, but currently it would be kind of hard or almost impossible to graph 3.5 every time. That means for each time I go 3.5, I got to go 1. So we got to represent it in a way that's a little easier. So why don't we do this? See that 3.5? If we multiply this by 10, that decimal point will move one spot over. So 3.5 will become 35. Once again, if we multiply 3.5 by 10, it will make 3.5 a whole number of 35. Now, if I multiply the top by 10, that means I also multiply the bottom by 10. And what is 10 times 1? That's going to be 10. Now this is easier to now graph. This is easier to graph. So now, my rise is a negative 35. So now I go down 35 units. I go down 35 units because it says a negative. So 10, 20, 30, 35. And my run is a positive 10. So now I go over in a positive direction, 10. So now I found my second point. My first point was my slope. My first point was my y-intercept at 50. To find my second point, I must count my slope. So therefore, 10, 20, 30, 35, that was my rise, and then there's my run. Connect the point and make my line. And that would be it. And once again, the y-intercept represents the initial amount on the card at 50. The slope represents the rate of change, a negative 3.5 per game played. Example 2, analyzing a graph. Many real-world situations can be represented by linear relationships. You can use graphs of linear relationships to visualize situations and solve problems.
Okay, so we're thinking about these lines, we're looking at their equations using the slope-intercept form. We're also looking at their graphs. Let's take a look at an application. And this is a very, very clean application because it involves a tub. Check it out. So, a bathtub contains 30 gallons of water. When the water drains from the tub, so the water is going to slowly drain out, it drains at a constant rate of 3 gallons per minute. The linear equation given by y equals negative 3x plus 30 actually represents the amount of water given by y that's left in the tub x minutes after the draining begins. Our mission is to try to graph this equation and then identify the x and y intercepts, which we did a little bit while ago, and try to describe what it all means. So here's a neat little graph that I've already started for us. This is the draining bathtub graph. So maybe I should have a little rubber ducky here. It's always good. By the way, whenever I take a bath, I do like to have my rubber ducky, and everybody's clean. So here we have, in the x-axis, we're going to represent time in minutes, and in the y-axis, we're going to represent the water remaining in gallons. And the equation that's given to us is y equals negative 3x plus 30. And notice, happily, that's exactly in the slope-intercept form that we've come to know and love. Because that means that we can just look at this and see that the slope is going to be -3 and the y-intercept is going to be 30. So where do I start my story? The story of this line, I'm going to start it at the y-intercept. So the y-intercept is 30, which means it crosses the y-axis at 30. Now let's get to figure out what the units here are. This is 9, and I have two little hash marks here. So this is going to be, I guess, 3, and this is 3 more, which is 6, and this is 3 more, which is 9. So each of these little marks represents units of 3. So 3, 6, 9, 12, 15, 18, and so forth. So if I'm at 27 here, if I go up 3 more, that would be 30. So this little mark here is actually at the height of 30. So I'll put a big dot there because we see 30 here. That corresponds to this. Now, I see that I have a slope of -3. Now, slope, of course, is always rise over run. And you might be saying, well, I'm not going to leave the ducky. You might say, okay, well, what's the run? You know, where am I running? Where am I running? Well, if there's no place to run, you're always running by 1. Because remember that if the slope is -3, that actually is -3 over 1. So 1 is the run. -3, though, what does that mean? Negative means we're going to go down. We're going to go down 3 and then over 1, then down 3 and over 1, and so forth, and you can start to see the line. So what would it be in this context? Well, let me show you a great mistake. So let's see if you can see my great mistake. So I go 1, 2, 3, down 3, and over 1. Put a dot there. That's actually wrong because we have to remember the units here. Remember, each of these little markings we determined was actually 3. So just jumping from here to here is actually a drop of 3 units. So we only go down 3, and then notice the units here. Let's check really fast. 1, 2, 3, 4. Each mark here is representing just 1. So I drop down 1 and over 1, and that's really dropping 3 and over 1. Do you see that? A little tricky. They try to fool us, but they can't fool us. And 2 points determine a line, but I can do more if I want. I can go down 3 and over 1. I can do that as long as we want, but then after a while, we could actually connect it all up. Now when you connect it all up, let me do this nicely here. Beautiful. You'll notice that I'm actually not going to continue the line beyond the axes. Notice I'm not putting arrows, and I'm not letting it go here or go there, because this is an actual real-world example which involves water draining out. And so we start with 30. So it doesn't make sense to have the arrow go up here. And once we get down to here, that means there's 0 water. That's it. It stops. So in fact, this is a very specific application where, in fact, we only look at this line segment that's given for this graph between these 2 axes. So how can we interpret what this means? Well, what we can say here is that the y-intercept here represents the number of gallons that we had at the beginning of this draining process. It was a very draining process, by the way. And so we had 30 gallons. That's what this y-intercept means, because this are units of gallons, 30 gallons at the start when time is 0. Now, what does this point represent? Well, this point actually tells us the time. The time that what happens? Well, the time when I have no water left, the number of gallons is 0. That tells us the moment when, in fact, the tub was totally drained. And what time is that? Well, we can count 8, 9, 10. So 10 minutes later, the tub is completely dry. And my little duck can get up and actually waddle away because there's no water left. Anyway, that's the power of connecting an equation to a graph, and we can now interpret what all these things mean. Congratulations on conquering lines. It was really, very fun and very clean. I'll see you soon.
Okay, let's take a quick look at the lesson tutorial. Now remember, the most important things about this lesson is you have to know how to graph the equation, but after you graph the equation, you have to interpret what's going on. You have to interpret what's going on. First, you have to recognize your y-intercept was at 30. And notice when it's at 30, x is at 0. And you had to be able to graph your slope, -3 over 1. So -3, that was down right there, and over to a +1. That's that. Okay, now right here, this is called your x-intercept. All right, now the y-intercept 30 tells you there were 30 gallons at a time of 0. That's at the very beginning. All right, and the x-intercept 10 tells you it takes 10 minutes for the tub to completely drain to 0.